strings at weak and strong coupling, please.
Can everybody hear me? Okay. So, hi to everyone. Let me join the other speakers by thanking the organizers, in particular Thomas, because all this thing of the pandemic and having to postpone the date and reorganize is a pain. I know it from firsthand, and probably some of you too. And it's great that at the end we could have this conference, so thank you. And, well, I changed a little bit my title. Before it was 40 strings of strong coupling, which, where's the pencil that you promised me? Oh, pencil, okay. So, the weak part is related to this paper, together with Stefano Lanza, here in the audience, Luca Martucci, and Irene, I don't know if she's around or not, because you never know. And the second one is with Max Wisner. And this, oh, very good. So the weak part of the talk, about the weak strings weak coupling, is related, well, is motivated by something that has already been mentioned and covered. It's one of the proposals that has triggered a lot of work in our community, which is the Swanland distance conjecture. I probably do not need to introduce you once again, because you have already seen a bunch of talks about it and how we make use of it and how it inspires several results and works. But let me just mention that, well, when you are in this asymptotic limit, you expect to have a tower of states, maybe several of one, but at least one leading tower that will signal a breakdown on effective field theory when you go along this infinite distance path. No? But the statement itself, the Swanland distance conjecture, doesn't give you the value of this exponential rate or the nature of the tower, okay? And there's a lot of activity that has been going on trying to understand these two items. So the idea of this talk is based on a series of ideas that has already been appearing in the literature, which is trying to translate some of the Swanland criteria or proposals that we understand less in terms of effective field theory into effective field theory objects. So examples are this paper by Clever and Palti and Draper and Farkas, and also it's very related to Dieter's. Is this going to disappear? Yeah. Oh, sorry, Dieter. Well, Dieter's talk today. Okay. And what we are going to do in this talk is to look at one particular object, which is four-dimensional strings. Why? Because we want to go for minimal supersymmetry. And in minimal supersymmetry, the BPS objects, which are the ones that we have better control over, are membranes and strings. Membranes give you an interesting physics, but strings give you, in my opinion so far, even more interesting one. Both of them, they have the feature that they are low dimensional objects, so the back reaction is huge. You cannot just neglect them when you go far away. But this annoying thing is going to be one of the most interesting ones. So what happens with the strings? Well, there's one particular kind of them, which in the paper we call EFT strings, which are four-dimensional fundamental axionic strings that have the property that draw the fields. I mean, you start defining them in a region where you have an approximate axionic symmetry, okay? So it's only broken by exponentially suppressed effects. And when you look at the solution and you approach the core of the string, this approximate symmetry becomes better and better and better until it becomes exact. They are fundamental strings, which means that they are above the cutoff scale. And the fact that when you go along this flow of fields, first you have angular, trivial angular dependence, so the non-trivial profile is only around the radial direction. And what you have is that, well, essentially the complex partner of the axion, the saxion, is the one that flows along this radial direction. You go along an infinite distance limit because, well, essentially along the end of this path, when you approach the corner of a string, you're going to realize an exact axionic shift symmetry. So what we all expect from quantum gravity arguments is that the effective field theory is going to put this at infinite distance field space, so there has some mechanism to shield itself from realizing physically this exact global symmetry, which is the axionic shift symmetry. Now, when you input this setup in practice, when you say, look, I want to have this axionic shift symmetry, I will have effects that break them, like given by some instantons, but you want them to become smaller and smaller and more suppressed. What you end up doing in a supersymmetric setup is with a structure which is a structure of BPS charges that have a conical structure very close to and actually related to what Fabian was telling us yesterday. Now, to get an idea of what this is about and what you can do with it, the best is to go for a class of examples. And the best one, I think, for this talk is the examples which are type 2A or heterotic compactifications on a Calabi-Yau threefold. We place ourselves a large volume, a weak coupling, so we have a bunch of axions, and we have strings, axionic strings charged under these axions. So some of the strings are the fundamental string, and some of them are NS5 brane wrapped on 4 cycles. The EFT strings are not any NS5 brane. They will be the NS5 brane wrapped on NEF devices. And we have the cone structure of the NEF devices. Now, out of this EFT strings wrapping NEF devices, there were ones which are more important for this talk, which are the generator of the NEF cone, which we call elementary EFT strings. The back reaction of each of them is giving us different independent ways to go to large volume, okay, when we follow one flow of one of them or the other, and while the other ones are positive linear combinations of them. And then we have NS5 brane, which we are used to them, wrapped on effective devices that are not NEF. These are strings. They have a life, they have a strings, but they are non-EFT strings. So when we consider the flow and we approach the core, we go to a region that is not weak coupling. Okay, we go to some strong coupling. Some instantons will become very important. There is a nice relation about the 4-dimensional supergravity string in M theory. It assumes the same conjecture, and well, there's also a bunch of papers that are related to this construction. But anyway, what I want to stress is that in order to extract physics out of this, one has to realize that there is a correspondence between 3 things. One is the EFT string back reaction. The second is the classical RG flow, how we understand the couplings of the string from the effective field theory viewpoint when we change the cutoff energy, in particular when we go to larger and larger energies. And third, the tension of an EFT string, the one that we are used to compute when we do dimensional reduction of a string in string compactifications when we move in moduli space. In particular, when we move along these field directions that are signaled by the EFT string flow as you approach the string core. Yes?
Could you also consider E-branes which look like strings in 4D or have the appropriate codimension wrapped around some internal cycles?
You could.
Yeah, but they are not interesting for you.
No, they are interesting. You mean strings in how many dimensions are we wrapping them?
Give an example. Take a D5 brane, which is an opterator on the 4 cycle. I mean, this is a S-module picture it had to be, or D7 brane, which is wrapped around the entire 6-dimensional space.
They are very interesting for me. So this NS5 brane, for instance, are examples of what you are saying. So I'm wrap them on some devices, some 4 cycle. They look like a string in 4 dimensions. And then you can do several things with them. You can consider them as being infinite strings in 4 dimensions, or you can consider them to be on a loop, like in here, which is interesting because it's like, well, it's a highly non-BPS thing. Forgive me, but it has a nice property that is self-regulating. When you go far away, this thing back reacts like 1 over R cubed, like a point-like thing. Very close to it, you have this back reaction of a codimension to object. Okay, so in this region, what you will see is this kind of BPS solution. When you are very close to the core, it looks like an infinite distance. Except that very close to here, depending on what the cutoff of your theory is, you have to coarse grain this solution, right? You will not have exactly this function. You need to cut off the Fourier modes up to this lambda. When you do this, you realize that the tension of the microscopic tension of the string, the one that we obtain from dimensional reduction, can be understood more or less as a sum of 2 terms. One of them is the energy that goes into the back reaction here, and one of them is the tension that you associate to the operator that describes your string in your effective field theory, right? And this is a RG invariant quantity. So when you change lambda, this guy changes, and this guy changes too, but the sum doesn't change. So when you go to very, very low lambda, you just see You see a point, there's no back reaction, there is no room for back reaction, you just see the tension of the string times the length, like we are used to when we talk about vibrating strings. And when you go to the opposite limit, when you go to infinite cutoff, you will see the full back reaction, and you see no tension on the string. Okay? And actually, you can relate these two, like by saying, okay, if I change the cutoff energy, is like if I was moving in moduli space, okay? Because of this relation in here, okay? This is a very imprecise equation because of this complicated back reaction of this string in a loop, but it illustrates that this flows that you see when you look at string close by and you see the string flow capture the physics up to some extent of moving in moduli space. They don't capture it entirely because, okay, we just have the capture is up to the cutoff scale, but it tells you something. And based on this something, we formulated two conjectures that are related to strings at weak coupling. One of them is the distant axionic string conjecture that tells you that well, essentially, I told you that because you, along the flow, it's like you were moving in moduli space, and or you can map it to a path in moduli space, and this should end in an infinite distance point. Well, the distant axionic string conjecture tells you that all infinite distance points are of this sort. You can create or generate all the infinite distance points by these kind of flows. So to each infinite distance point, there is some axionic shift symmetry that you are associating. And then, as it came from the previous pictures, when you approach these points in moduli space, you should have a string that becomes tensionless. This will signal an EFT breakdown because this is a fundamental string. If it's below your cutoff scale, something really should go wrong. It doesn't need to be that the vibrational modes of the strings at the tower of states predicted by the Swampland distance conjecture, but what the second conjecture that we formulated proposes is that there is a neat relation between them. And the neat relation is this one, where you have an integer that relates the string tension as you go along its flow and the mass of the tower of states. So the interest of this, or one of the main points of these two proposals, is that they give you a very clear link to the Swampland distance conjecture. The only extra thing that you need is the weak gravity conjecture for strings. The computation is one line. Essentially, first you need to relate the distance along the flow with the physical charge of the string, which is this formula here. Then you need to use the properties, this just using like PPS, now supersymmetry, or having a kinetic terms given by Keeler potential that you derive this relation. Then you use in here the weak gravity conjecture for strings, and this already tells you that the exponential decay of the string tension goes like exponentially fast to a tensionless string. And finally, with this relation, you get a precise relation between the rate of exponential decay of the tower, the extremality factor, and this integer weight. And then finally, you use this result to say that, well, for all points, you should see this kind of behavior. Very good. So that was the weak part. And now the next question is, what happens if you, okay, all this is based on the fact that I'm in a region which is a wiki couple where we have an axions, approximate axions, where I have all these things. I have a lot of relations. I have a Keeler potential that is simple, that only depends on axions up to some exponential suppress, blah, blah, blah. What happens when I go away from there? What happens when I go away from the infinite distance limit, when I go to the bulk of moduli space, which is always the tricky part, the things we know less, and the things we fear most. So the first question is, can we extend the solution? I have give you a local solution. This is all a local solution and a map from a disk to moduli space. Can we extend it to a full thing all over the complex plane? Does the tension stays in this range, which is the ones that we associate to fundamental strings? Does it not go super Planckian? Because if you just extend this logarithmic naively extend this logarithmic thing, it thinks it will blow up. And finally, can we learn anything about the bulk of a moduli space with these objects? So what I will try to convince you is that these two questions, they should have a positive answer. That will be some conjecture again, but I will try to give you some evidence. And then the hope is that you can say something about the third. OK. So any questions so far? OK, let me get into the, no. What happened here? OK, no, this. Let me get into the strong coupling part. So the first question is, can we extend the solution? And the simplest thing to extend the solution is to say, instead of having a local solution around a disk, around the core of a string, I want to extend it to the whole complex plane. Okay? Then even if it's a string on a loop, then I can manage to encode as many part of the moduli space in this disk that I was telling you in the previous picture. Extending to the complex plane basically goes back to this seminal paper of Green et al., in which they talk about string cosmic strings, and they push the theory for a very particular example to the limit. In this setup, we'll have an action like this, and we will have a metric ansatz of this sort, where this is a holomorphic function, this f, and essentially the solution is codified in this holomorphic function for the complex plane to the moduli space. Near the origin, we should have an EFT string solution, which means that locally things should look like this with this log behavior. And then we have a bunch of parameters that appear already in the EFT string solution that we need to understand globally. And that will be part of the talk. Now, the particular case, the F-theoretical ones that you all know and love, involve a guy that will be our friend, the axial dilaton, and a simple solution given in terms of the J invariant. Okay? This is one particular solution in which the core will be at the origin. And as you can see, already by expanding the J invariant, you get something that is very, very similar to what we were saying. Of course, what we want to do now is to do it for more general theories, with more general Kerr potential, with more general fields, with more general kind of strings, like the type 2A that I was talking to you about. One systematic approach from where we got a lot of intuition is try to build general solution by identifying building blocks. This is something like, well, non-EFT theory, building blocks, you patch them and you construct your solution. In the case of the F-theoretical example, you have two of them following Bergschuh et al., which is this 1A and 1B solutions. And here, how you describe the solution is in terms of, well, the J invariant is this quotient where it appears 3 parameters, which are the images of the J invariant of the singular points in moduli space, no? The orbifold points and the infinite distance point. Now, from our 4-dimensional viewpoint, which is the one that we are pushing, this looks like a string course that hosts field monodromies when you go around them. Okay? So this guy is the EFT string, and this will be another string that gives you a finite of the monodromy, and this will be another one. So for the 4-dimensional theory, these are string cores. This will be the second configuration. And then an interesting aspect of this toy example is that in these two cases, we have a localized tension in the string core. There's in here the tension, as we were saying about the EFT string, when you approach it, you get a tension that goes to 0, but not for these guys because it's a finite of the monodromy, and the tension is given by this formula. So then also, if we want to have a finite energy solution, we should input this string cores not in C, but in P1, right? Because we want the 1-point compactification of infinity. Otherwise, we will never have a finite energy solution. Then this implies that the monodromies might cancel, which restricts the kind of solutions that you can have. And then also it gives you a way of understanding what is going to be the total energy of your system. Because the total tension of the system is going to be stored in the back reaction and each of the cores, okay? And they should satisfy this formula because you are going to cancel all the charges, or you should cancel all the tensions, okay? So what happens in this picture of these people in here is that they say, okay, I have one guy that has negative tension and set it to a spatial infinity. This is a non-physical string core. And because the tension cancels, I know what the total tension of the system is going to be by looking at the localized tension of this object. And when you do that, in this 1B solution, you get something like this. And you can see here, this is the energy of the back reaction, this is the localized energy of this guy, and this is the localized energy of this non-physical guy. Very good. Now, what is interesting for me in these two examples is that comes out with an object that is going to appear in the more general case. That's why I'm bringing it here. And this object is what we call the regulator strings. Because if you look at this global solution that has horrible form, but we can encode it in the chain variant, is very similar to the naive extension of the string solution that I was telling you before. The only difference is that these two things, this Z1, which is the location of the regulator of one of the string cores, coincides with this parameter Z0 that we identify with some of the parameters of the local string solution. Okay? So essentially, what's going on is that these extra string cores are codifying the parameters of the local string solution, of which I made this big mess at the beginning. I told you I can extract all this physics out of the local string solution. The local string solution has some parameters. From the global viewpoint, these parameters have to do with where this guy is sitting in complex plane. And we call them regulator strings because the position signals a strong coupling regime. When we approach here, we see one of the refold points of the moduli space of the acyl electron. It's no longer with coupling. When you take into account the monodromy of these two cores combined, you no longer see a unipotent monodromy that you associate with this axionic shift symmetry. You already see a finite order monodromy. And at the same time, the presence regulates the log divergence that you will have if you just naively continue the back reaction of an EFT string. And perhaps more interesting, when you want to consider this configuration of the loop string, and in here you want to input some boundary condition that is a strong coupling, these two guys are going to appear together. The solution tells you there will be a second core related to this core in here, and should appear as some, when you go to strong coupling, you will not only see the EFT string solution, you will see a complicated solution, and these two objects will form a bounded state. So your spectrum of a string is going to change when you go to strong coupling if you want, and it's not the EFT string that survives, but this bounded state, okay? This is part of life of the strings. Now, what is the general picture? As in this F-theory-like example, the regulator string should also happen in any string compactification that has astyonic strings when we go away from the perturbative limit. We need them to create this global solution into complex plane that we can do one-point compactifications. And instead of being these orbifold points of a two-dimensional moduli space, they're going to be singular devices of a moduli space that are going to be intersected by the image of the string solution. The string solution maps you the complex plane into a two-cycle in moduli space. Now, there's one important caveat. Unlike in the example that I was telling you about, they cannot host a localized tension because then this will break supersymmetry. This will not be this. That's in the F-theory-like example. That's something very clear. Because you will not have a K3, you will have a vanishing of or a pole of the 2,0 form. And so the only thing that we allow for acceptable global solutions are regulator strings with unipotent monodromies, which means that when you approach them, they host zero localized tension. The only one that can have a localized tension is the non-physical string at infinity that has a negative tension. So we can have conifold strings, we can have conjugates of EFT strings that do not commute with them, but we cannot have things that have localization at a spatial finite point. Then there can be a lot of regulator strings. It doesn't need to be one like in the previous example, but they need to satisfy this condition. You have the EFT string monodromy, then you will have a bunch of regulator strings, and actually, when you multiply these monodromies, they will be equal to the monodromy at infinity because we need the whole charge to cancel. And of course, the back reaction of the full solution will be related to the tension of the string at infinity. Then the next question is, with this setup, can you always find a global solution such that this is sub-Planckian? So it's below 2 pi mp squared, because if it's not, then you will start like bending the space, and then you going to infinity doesn't make any sense. No, so in order to have things that go all the way, we want global solutions that have a sub-Planckian tension. And the next conjecture, and I promise the last one, is the strong EFT completeness conjecture. That tells you that essentially, yes, if you look at elementary EFT strings, the building blocks of the world of EFT strings, you should be able to find a global solution that is of some Planckian tension. So it will go all the way to some point in Boltzmann space. One important caveat here is that for this, I am looking at compactifications where I have an actual moduli space. For all the weak version, you could think that you are in a very localized portion of moduli space and a very high energy, so that if you have a potential, it doesn't make any strong effect. But for here, if I have a potential, even if it's non-perturbative, things could change completely, so I will not make any claim. It will be very interesting to extend it, but we cannot make any claim right now. So what this conjecture means is that if you have a local EFT solution, there is no obstruction towards the extension. And if it's an elementary EFT string. Also, it tells you that the local parameters, the things that you see locally, are the parameters of the global solution. You don't get extra global parameters. And then each global solution will correspond to a two-cycle in moduli space intersecting a divisor at infinity. And what we find in our examples, that we don't know if it's general or not, we have no clue, is that this solution for each EFT string is that foliation of the moduli space. So really, you sweep the moduli space when you look at all of these solutions. Okay, that's interesting. Okay, so to motivate why we propose this, let me go back to the previous class of examples, which is type 2A or a geometric string with a standard embedding on a Calabi-Yau threefold, and look at the NS5 brane in F divisor, which are the most interesting ones. So now we don't want to be in the large volume. We don't really have this axionic shift symmetry related to the B field reduced over 2 cycles. Now we are going to include bullshit instanton corrections that are going to mess up the whole effective theory. So what's the idea to try to extend the back-reactive solution? So one way of doing it is to think of the string back reaction, parameters of the string back reaction in terms of a gauge linear sigma model related to the Calabi-Yau threefold. And when you do that, for each Keller modulus, you have a phi T lopulus parameter in your 2D theory that for large imaginary values flows towards a region in which you're describing a nonlinear sigma model related to the Calabi-Yau threefold, and essentially this phi T lopulus parameter is identified with the Keller modulus, complexified Keller modulus. Away from this region, well, this is not going to be true, but there's going to be a one-to-one mirror map between the space of phi T lopulus parameters and the quantum Keller moduli space. The interesting thing is that following the work of these people, one can argue that the back reaction, the NS5 back reaction, is described by a very simple log bar reaction in the phi T lopulus parameter, okay? Which is very reminiscent of the kind of local back reaction that I was telling you about. The thing is that this is global and exact. All the mess of the non-perturbative corrections is encoded in this mirror map. But in the world of phi T lopulus, it's kind of simple. Of course, when you go near the string core, you're going to recover the previous, the previous solution plus corrections. But when you go away, you have a very different thing that you can encode in this 2-cycle in moduli space. And you see that the local the parameters that I was telling you about, this continuous and discrete parameters, is that the string charges get mapped into parameters in the global string solution, which is very nice and is reminiscent of all this work trying to reconstruct things from the bulk from boundary data, led by Thomas and friends. I mean, I don't have any particular to say about that, but it's like it seems that things go in the same direction. So rather than go into say general things, let me go for an example, which I think is quite illustrative, which is this degree 18 hypersurface studied by Candelas and collaborators, in which you have you have an F cone with 2 generators, and then you can, of course, wrap your NS5 brane in a linear combination of these guys. So in this case, the profiles will look like this when you write them in terms of exponentiated phi-plus parameters. And the interesting thing is that here you see the appearance of of regulator strings in terms of the discriminant locus, which is the surface where the theory becomes singular, and this one. These are the, of course, this is a real projection, but these are divisors in this complex two-dimensional space. And this is as simple as this. The elementary strings, the profile looks like this. So they start from here at infinite distance. I'm going away from infinite distance. They start from here, they go blah, blah, blah. They, oh, I cross one regulator string, blah, blah, another regulator string. This is a string at infinity, okay? And this is how you're supposed to build your global string solution. The divisors, they are attached to some conjugacy class in the monodromy of the monodromy group. But the representative you need to choose so that this rule, this cancellation of monodromies is achieved. The long story short, you can do it, and then you end up with this sort of formula, which you see that here you have, if you have E1 equals to 1 or E2 equals to 1, you get something that is subplankian. You can also do it for some examples. We have not done it an exhaustive, but looking at this example, it looks like you really can do it. Or at least that's our proposal. One interesting thing is that you can also look at these non-EFT strings that were very mysterious for us, and they are still very mysterious for us, by looking one particular NS5 brane wrap on some particular divisor. Let me take an effective divisor that is non-EFT, like this particular combination. And then what we find is that if we want to have a solution where all monodromies cancel and things look fine, we cannot have a naive profile that would be this one, the black one, because then the monodromies will never cancel. You need to deform it to have a multi-center solution, because this is not an elementary string. You can have the multi-center solution, such that we have a centering here and centering here. And then, because you do that, you cross this singular divisor twice, and then you input the monodromies that allows you to cancel all the charges, and things make sense. Now, this looks a lot like the F-theory-like thing, because you go to a region of a strong coupling, and you see something that looks like one core becoming 2, but it's not as nice, because this guy in here has a negative localized tension, and this was forbidden. So we don't know what's going on, and we are supposed to see things microscopically. So I don't know. I don't know. I'm lost. So any proposal is welcome. But it really looks like this is going to be general for non-EFT strings. Now let me come to the geometry at least. So in this case, there's also a geometric interpretation. In other setups, no, but in this one, you can use mirror symmetry to, instead of trying to fiber the complexified Keller moduli space, to fiber the complex structure moduli space. And then what your solution should be, then you can stay at large volume all the time as you want, and what your solution should be is a Calabi-Yau 4-fold that is a vibration of Calabi-Yau 3-fold over a base that you could, for instance, take to be a P1. When you try to do this, then you will consider, for instance, this hypersurface equation when you want to describe the vibration, and you can use the large complex structure limit to make the identification between these exponentiated phi-plus terms and the parameters, the complex structure deformations, okay, with these powers. And then, by turning the crank, you realize that EFT string with these charges will correspond to a vibration over P1 with Q2 constant, and this one will correspond to a 1 over P1 with Q1 constant. So essentially, in a similar way to the to the Green et al. Setup, what we see is that we are fibering clavicle threefold, not over a P1. The elementary string is not fibering over a P1, but over an orbifold that have the curvature that is a fraction of the P1, that have a singular point that corresponds to the point at infinity of our solution. And essentially, the elementary string is about this fibration. So if you want, what the conjecture was saying is that you can always do these kind of things for elementary strings. Really? Oh. Oh, okay. I thought it's 40. Oh, okay, okay. Well, I'm done. I thought it was less. Okay, very good. Okay, but okay, never mind. So let me conclude, because you are all hungry and you want to enjoy the dinner after, of course, only after Sarah's talk, of course. So the summary of what I was trying to tell you today is that we start looking at these local EFT string solutions because they are physical objects that encode information of limits of infinite distance, okay? And the fact that they are physical objects allow to do one thing, which is input one extra property to them, like the weak gravity conjecture. You see, if you look at them only from the math viewpoint, like adding this weak gravity conjecture, you a priori would not think of it. I would have not thought of it. But when you try to model these limits that we see in model space in terms of physical objects, you can add extra structure to them. So that was the first part of the talk. Now the question is, okay, well, like I'm looking at this particular solution and like I'm sweeping under the rug what happens at long distances, you can try to go in the opposite direction. Do I have an object, even if it is BPS object that extend all over the space? It's going to bend the space-time. It's going to do all kind of crazy things, but is it a physical object that I can play with? It will have a tension that it will make sense in my effective field theory, blah, blah, blah. And this all amounts to extending the solution over the complex plane. What our analysis suggests is that you can do it without getting a divergent tension. You can even get a sub-Planckian tension. And for that, we use the intuition that comes from F-theory-like constructions that highlight an object which is this extra regulator strings that signal that you are already at a strong coupling, and is some object that you need to have in order to build your global solution. Okay, so anyone with intuition from F-theory will understand what these objects are. So what we propose is that you can do it with some Planckian tension, and geometrically for this particular case that we were saying, or if you want, when you try to fiber complex structure parameters, complex structure modular space over an orbifold of P1, what we will say is that you can always do it. So you just say the generators of your world of strings, which are the elementary strings, you should always be able to fiber this guide, not over P1, but over an orbifold of P1 with some therefore with some Planckian tension. So, thank you.
Thank you very much, Fernando, for this nice talk. There are questions.
Nice talk. Do you have any reflection on why these tensions turn out to be rational? Or do you have any ideas why, if there's any, I mean, in all the examples, you have these orbital type things, or like, in the case where you have 124 and so on. Is that something you think is the principle of compound kind of things, or do you have any counterexamples?
So you want them irrational, or
I'm asking, why are they always rational, right?
Well, but my very naive intuition is that they are an orbifold of a P1. I'm doing the fibration.
You're talking about from construction, right? I'm saying from bottom up. What does happen if you're not rational? There will be a problem. It sounds like it's not.
I don't know, but
Since we don't have a single example of that, like, it must be good reason.
it will go against my intuition because of this cone structure where.
The question is
No.
not that it's possible. The question is why, from effective field viewpoint, or quantum gravity. I mean, from what goes wrong if it were not.
But I'm not sure that non-BPS strings
So you're talking about the localized tension? Well, okay, yeah, I guess because it's the same thing. Well, so you want to have a monodromy that is irrational? Is that, I mean, no, okay, but
No, I'm just saying that why is there a good reason that it doesn't appear in super gravity? And if so, and if it doesn't appear, can we use it to restrict some other thing? I'm trying to push it at something useful.
I think, yeah, I think these irrational monodromies will look awful. I don't know which kind of fields would make sense that would transform into them. It's
So you wouldn't know what goes wrong with irrational.
no, but yeah, it looks awful. I mean, well, yeah, okay, no, it's about intuition of dualities. I don't see how we can have a world of dualities with irrational, but nothing beyond that, yeah. No.
Other further questions? Yes.
You mentioned that the EFT strings are supposed to live in the left cone.
Say it again?
You mentioned that the EFT strings are supposed to live in the left cone.
Yeah.
Can you allow the entire extended character? I would think that the movable objects would be the ones
I'm not sure. So what do you have in mind exactly?
So if you have an extended character that's made of many phases and you flow from one to the other, I would think that the spectrum of the EFT strings stays the same.
Okay. So in the theoretic type 2A, no. But in type 2B, you would go to the extended current cone. You would do all kind of flops. I mean, the important principle here is that the boundaries of your cone need to break the axionic shift symmetry. So in here, when you are talking about world-shift instantons, you go to the boundaries of the color cone, you're in trouble. If you're talking about different axions, like for instance C4 actions in 4 cycles, then going into the boundary of the color cone doesn't break the axionic shift symmetry. The 4D doesn't care too much about it. So then with the flops and all the flop universe becomes relevant, and you go to extended color cone.
Other further questions?
Are they stable, or do they have like strings have instability?
The infinitely extended ones? Yes. Say it again? They are BPS. I mean, the ones I'm talking about, if they are infinitely extended, the ones with the global solution, they are BPS. Yeah, yes, should be BPS. Yeah.
And then if we get moduli space, then can they not BPS particles they decay?
No. Non-EFT string, yes. EFT strings, they are not decaying. So it's like a guy wrapped on a NEF divisor. It will not decay. They should be. Well, I mean, up to this bound with the regulator string, whatever you want to call it, they are stable. I mean, so just think. Well, that's the regulator string. That's a regulator string. So the statement is your monodromy is no longer your naive monodromy. It gets complicated because you have a bounded state of EFT string and regulator string. If you want to call it a decay, yeah, it will be like a Cyber-Witten thing, yes. Yeah. It's quite analogous to Cyber-Witten-like physics. So if you want to think in that terms, yes, there is a dance of strings, yes.
Okay, there's maybe one last question over there.
So in order to derive the distance conjecture, so in the infinite tower of states,
Yes.
is there an argument that these CFT strings will give rise to an infinite tower of states, or it could happen that?
Well, that was some of the discussion we have with Timo and friends. If they are not critical, we don't really have a microscopic description why. But something should go wrong because, like the idea is that these are things that are magnetically charged under a fundamental axion. If you start resolving what these things are in your effective field theory, and this is fundamental, it's like an anti-definition of fundamental. So something should go wrong. In the examples that we see, which trigger us to make these two statements, in particular the second one, it matches very well with the emergent string conjecture. We either see critical strings or Kaluza-Klein towers. We don't have a sharper statement beyond that. I mean, it would really look weird from our quantum gravity intuition if something else happened. But a priori, yeah, I cannot say more.
All right, I think it's time to move on. So let's thank Fernando.
Thanks, everyone.